Hello everyone. Recently I've seen a lot of takes on the sinking of the deep sea submarine Titan, but all of them have been by seamen or journalists or equivalent people, former employees. I thought that I would give the perspective of an engineer, which I actually haven't seen in these couple of days that the drama has been unfolding. So what we're talking about is the hobby sub Titan. That's what I call it. It's a small deep sea submersible. Has a few people on board. It was lost at the wreck of the Titanic, where they've been doing tourist visits. Yeah, it's been 2 to 3 days, I think, since it sank and since it's been on the news everywhere. 5 people aboard, I think, all of them rich billionaires or almost billionaires. Cost $250,000 US dollars per ticket. Not exactly a fun for poor people. They like to call themselves explorers, like Richard Garriott, but like buying for a ticket to go to space or the ocean or Mount Everest, and having other people, having Sherpas carry all your stuff while you take pictures and press a button or something, that doesn't make you an explorer or a scientist, or it just makes you a rich tourist. The submarine was made by a billionaire wanker called Stockton Rush and his Silicon Valley tech startup OceanGate. That's kind of the vibe that I've been getting from all the PR that they've put out, from all the videos, all the news articles I've seen. They don't like to think of themselves as a traditional ship builder or anything like that. They're a high tech new wave startup bad boy thing, which not something you want to hear when you're going to the bottom of the ocean. The Titan is not technically their first sub. They've had, I think, 2 before. Their last one was a lot less ambitious, though. It had a steel hull and it only went to 500 meters. And I think they've got like help designing it from universities and so on. So not really that closely related to this new guy. That's bigger, goes deeper, made of mostly of carbon fiber. The last guy who made a submarine in his garage raped, murdered, and dismembered the first woman who came on board. So we're not talking about a hobby or an activity with a brilliant history exactly. People who build private subs tend to be a race of their own. Right here we have the CEO Stockton Rush showing off the high-tech control system of his future submarine. As you can see, it's a 15 euro Logitech third-party controller with a steering wheel and a turbo button, and it's actually wireless. They didn't even bother putting in a wire in there, because it's the future, man. Wires are old hat. They're not for brave startup future men like him. I don't think they're alive anymore, and I'll get to the reasons why I think so. But the consensus right now, I think, is that it's stranded somewhere, either on the surface or on the bottom of the sea, and they're running out of air and food and water and temperature and life, So the general narrative right now is that there's still a chance to save them, and there's a lot of ships, a lot of subs, a lot of helicopters from a lot of different countries right now trying to do that, racing there to try to find them with the little time they have left. I don't believe that's necessary, but I guess it's good PR. Usually I guess a coast guard or submarine rescue team, like, they don't get a lot of press. They're just around, not doing much. So getting their names and faces in the papers is, I guess worth it, no matter what the actual chances of finding them alive are. And it's actually not a very easy operation. It takes hours just to descend to the depths, so unless they've floated back up to the surface, it would be a very long and difficult operation to find them from the bottom of the sea, even if they had more time, which right now they're pretty much running out of it. I think they had like 4 days worth of oxygen, and right now we're like under 12 hours or something like that of calculated oxygen remaining. And of course a lot of people are blaming things that are obvious, things that are funny, things that they can see with their limited expertise, and one of them of course being their high-tech control device right there on the right. But a lot of other stuff, like the manufacturer of the cupola in the front, like, they didn't want to certify it, or they didn't certify it to those kinds of depths because it was, I guess, just wasn't up to their standards, their design practices, or the established sort of requirements for such cupolas. So, but if it came from a subcontractor that at one point thought that it might withstand 4,000 meters, I'm thinking that the reputable subcontractor is probably not the one responsible for the loss of the submarine. Here we have their lead stress engineer, diploma engineer, Sam Hyde, looking at his calculator, being very pleased at the results, whatever they might be. And behind him you see the manufacturer of the pressure hull. And at this point, if you have some experience with carbon fiber structures, you have probably gone very quiet. There's a bit of a pregnant pause hanging there. I'll explain to the rest why exactly, but the fact that they put this on their webpage is kind of telling. And yet this is the central section of the submersible. It's capped on both ends by a hemispherical titanium cupola. I don't think those are the reason why this thing probably imploded on the bottom of the sea. I think that this section that they made themselves is the part at fault. I read some interviews. Like, I haven't done, as you saw from the title, I haven't done a lot of research. This is just something I did quickly to bring to light something that I noticed, very quickly. but from what I read, the CEO pretty much designed the thing himself. I don't know if he has any sort of expertise or education from the area of structural design, of systems design, of submarine design, or manufacturing, or anything even related to that field. And apparently he doesn't want any old white guys working at his company, which is a bit difficult because most of the people who know how composite structures are made and designed are probably old white guys. So, especially in the United States. But even honestly, it might be a majority just in the entire world, you know. Especially if you take the Japanese into consideration, as we know they are honorary white people too, so they kinda tilt the scales a bit. So, to give you a little bit of background theory, I'm not going to go into any sort of detail here, but we have something called a classic laminate plate theory, and that is a very basic, very simple theory that we use to make the first pass calculations for composite structures. And it basically means you take all the different materials that are in different orientations and you just average them out. And then you treat it as like a single element, whether it's like a two-dimensional shell element or a three-dimensional sort of volume element. And the main thing here is that in the classical theory, effectively what's carrying all the load is the fiber, and the fiber only in the lengthwise direction. So this seat belt that they're winding around a drum is tape of pre-preg carbon fiber impregnated with epoxy, and they just lay there and then let it harden, either just on its own or in an oven. And as you can see, all of the fibers are just wrapped around the barrel. You know, it's all oriented in the tangential direction. You know, tangential means in this case just around the cylinder. And what's sort of notable, what's the first thing I noticed, is that is fine for a certain special case. Sometimes when you have a long pipe that, you know, usually braced, you know, there's some sort of brace, some sort of structure that holds the pipe in place, and that sort of carries the axial loads on the pipe. So when you talk about some long pipe, like a long oil pipe, you might not necessarily need to consider the axial component too much, because it's carried by the surrounding structure. But in this case, this is a short length of pipe and it's capped on both ends, so there is substantial axial load on it. And axial in this case means, you know, in the front and back direction of the submersible. And again, according to classic theory, you know, what's most important is the lengthwise direction of the fiber, and there's no fiber in the axial direction of the submarine, which just looking at it with your forehead is just unacceptable. You know, that this is not how you would design something like this. You know, and the fixture they have, the jig they have for this pipe section, it doesn't even allow you to lay down any tape in the axial direction of the submarine. It there's flanges on both ends, and usually even if you end up cutting it into a pipe section, you actually wrap it. It's called filament winding or winding, the process where you wrap something around a cylindrical thing like that. And it usually has hemispherical sections on both ends when you're winding the tape. Even if you end up cutting it to a pipe, you kind of want the sections on the ends because it allows you to hook the tape. Right now you can only really go like around, and there's like a 1 degree angle to the tape when you're winding it. If there's hemispherical sections at both ends, you can sort of hook it around, and you can bring it at a very severe angle, and you can get some lengthwise components there, so you don't have to like hand lay any fibers like in the axial direction of the cylinder. You can just hook it around and do it as a part of this winding process, and that is why when you look at like rocket motors or something, it has sort of this rhombus pattern to it, because it sort of goes left and right, with a very large left and right axial components in the plies, and layers of composite are called plies. I put this picture here, sorry to the people in the source who had to be part of this nightmare, but basically when you cut a composite in half, that is what you see. The white stuff is the matrix. The matrix is the engineer name for the glue, and the black spots are the fibers. And here you can see obviously why this is a problem, that there is no axial component in the winding, is that you just kind of have like spots of fiber, and there's no like path. They in compression, yeah, like those fibers are scrunched together, but in the conservative practice of engineers, you don't even take really the strength of the fibers in the transverse direction into account at all. You just, if the fiber sideways, it doesn't matter. Like the epoxy matrix is just really the only thing you consider at this point. Roughly speaking, it's not that simple quite, but just looking at this, it's shocking. It's a small miracle that it even went to that depth once, let alone something like 10 times before it imploded. I'm gonna get just a little tiny bit into the maths. I did not any sort of sophistication, just something I could do in an hour on an old sort of calculation that I could plug new numbers into. Assuming classical theory and a thin wall scenario, neither of these are appropriate for complex situation like this. It's loaded both in hoop stress, and that's called like that's the tangential stress component, that goes around the pipe, and then there's the axial component that's in the axis of the pipe. And then this is not thin wall. Obviously it has 5-inch thick walls. The thickness of the wall is like 1/10 of the interior diameter, and those are just sort of assumptions from pictures that I took. I don't have the accurate numbers for the diameter and the length. The wreck of the Titanic is in the depth of 3.8 kilometers, so that's what I used. But yeah, these are not appropriate. This is just very quick sort of proof of concept back of a cigarette pack kind of calculation to sort of give me an indication of what's going on here. And my first impression was pretty much spot on, like the sort of failure criterions. Composites are very complex creatures. There's when you estimate like when it fails, there's a lot of different ways you can estimate that, but sort of all the obvious quick ones that I threw at it, like what's the maximum strain of the epoxy, or what's the composite strength compared to the stress it experiences. And I basically came to the conclusion that in the hoop stress direction, in the tangential direction, we had a factor of safety of about 5, which is, perfectly appropriate for a deep-sea submarine. But in the axial direction, like the different criterions converged at around less than 1, which, like if it doesn't get to the finish line when you're making a simple calculation, you should have given up before you even went into detailed design, much less manufactured the parts, much less put people inside. So it kind of tells me that their diversity hire engineers, if they even had any engineers, kind of obviously didn't know what they were doing. Like this is this is a sort of complex system, complex mechanical structure situation scenario, and you would ideally have PhDs and university professors to take a look at a situation like this. But if the cigarette pack calculation arrives at it's not gonna hold, then you are in the woods. Axial load of about 130 megapascals, which is about the strength of good epoxy in compression, which is pretty much, when you see something like that, when sort of coincidences happen to perfectly line up, where sort of the simple assumptions you make arrive at the conclusion that it's at the very point of failure, it's on the very edge of failure at the depth of the Titanic, and that's where it was suddenly lost. And when it did dives to that depth before, the submersible apparently had some structural damage, which composites aren't really that vulnerable to. Metal has fatigue, but composites tend to be very long-lived. So if usually they last for a very long time without problems. Usually, if you follow best conservative engineering practices, that's the case. And one thing that was pretty shocking is that since it's effectively, there's no fibers in the axial direction of the hull, if you just treat it as solid epoxy, it may have compressed, it may have strained in the axial direction by 4 centimeters or even more, because once it starts failing, epoxy is a plastic, it doesn't like suddenly snap, it actually like stretches. So that kind of gave me, I started thinking, first of all it horrified me, and from then on I thought that if they just had like some sort of an electrical box maybe installed on the wall on the inside, it probably would have bent. They would have come up to the surface and they've been like, hey, our electrical box has a set to it. It's bent. Like what's going on here? But because it's, I didn't have any pictures here, but it's just a straight tube on the inside. It has like a rubber mat on the floor. It does have like a floor structure, some sort. I don't know how it's attached to the hull, you know. But yeah, this is all very frightening and concerning. Here's their test pilot, you know, being very smart and driving the submarine when it's not underwater. You know, the CEO wasn't quite that smart. I think the center section of the pressure hull failed in compression. I think the actual point of failure, if they ever find the submarine, is probably like near the end caps, because that's what always happens. You know, the failure is somewhere near a feature, because there's always some sort of a stress concentration point there, and even if it's minute, it's still enough, you know, to begin some sort of failure. And once you're at 4,000 meters, you know, like any leak of water is gonna be like a water jet, you know, cutting you in half. And even if you aren't cut in half, the failure of the pressure hull is probably quite rapid. So, you know, the onrushing water is just going to crush you, and even then, like, you're on the bottom of the ocean, you're just going to drown if nothing else. I think that since they dove to the Titanic wreck, they're probably gonna eventually find, someone is probably eventually gonna find the thing, but I don't think they're gonna make it in time to reach their like 96-hour oxygen limit, or whatever it was. So yeah, I've nothing else to add. Cheers.